Money may shape our world, but physics shapes our reality. And among all the breakthroughs that science has ever produced, few have rewritten our understanding of existence as profoundly as Einstein's theory of relativity. Today we're exploring the discovery that changed time itself, how one young patent clerk overturned centuries of beliefs and showed us that our universe is far stranger and far more flexible than we ever imagined. This is the story of relativity, what it actually means, why it matters, and how it transformed everything from GPS satellites to the way we see the fabric of space and time. Part 1. Before Einstein, the old view of space and time. For most of human history, space and time were considered absolute. They were constants, unchanging, universal, the same for everyone no matter where you were or how you moved. This idea dates back to Isaac Newton. According to Newton, space was a rigid, three-dimensional stage where events happened. Time was like a universal clock, ticking uniformly everywhere, and both existed independently of each other. This picture was simple, intuitive, and it worked well enough to explain most of the physics known at the time. But, as technology improved and scientists began measuring the world with greater accuracy, cracks began to form in Newton's perfectly ordered universe. The biggest crack came from light. Part 2. The speed of light problem. By the late 1800s, physicists discovered something strange. The speed of light always seemed to be the same, no matter how fast you were moving when you measured it. This made no sense. Imagine you're on a train going 50 miles per hour, and you throw a ball forward at 10 miles per hour. Someone standing still sees the ball going 60 miles per hour. Speeds add. Simple. But with light, this never happened. If you shine a flashlight while running, the light doesn't go faster for you and slower for someone else. Everyone measures exactly the same speed, about 300,000 kilometers per second. This was impossible under Newton's laws. Physicists tried to fix this with all kinds of theories, like the idea that light traveled through a mysterious invisible substance called the ether. But experiment after experiment failed to detect any trace of it. Physics had reached a point where something big had to give. Either the speed of light wasn't constant, or our entire understanding of space and time was wrong. Then, in 1905, a 26-year-old patent office worker sent in a paper that quietly detonated the foundations of modern physics. Part 3. Einstein's radical idea. Einstein proposed something bold. The speed of light is constant for everyone. And because of that, space and time must adjust themselves around it. In other words, the problem wasn't light. The problem was our assumption that space and time were absolute. Einstein argued that space and time are not separate things. They're part of a single four-dimensional fabric called spacetime. And spacetime behaves in surprising ways when objects move quickly, especially at speeds close to light. This became known as special relativity. It produced two shocking predictions. 1. Time slows down for moving objects. The faster you move, the slower time passes for you relative to someone standing still. This is called time dilation. 2. Objects shrink in the direction of motion. This is called length contraction. These ideas sounded ridiculous at the time, but Einstein's math was airtight. More importantly, his predictions matched what the speed of light measurements had already shown. But these were just the beginning. Einstein's work didn't merely fix the problem. It opened the door to an entirely new reality, one where time itself could stretch, bend, and behave differently depending on how you moved. The universe suddenly became a flexible place. And Einstein didn't stop there. He wanted to understand gravity too. Part 4. Einstein takes on gravity. Newton had described gravity as a force that objects exert on each other. Einstein thought this explanation was incomplete. He believed that gravity wasn't really a force at all. Instead, Einstein suggested that mass bends space-time, and objects follow the curves in this bent space-time. Imagine placing a bowling ball on a stretched rubber sheet. It sinks down and creates a dip. Now roll a marble nearby. The marble naturally moves toward the bowling ball, not because the bowling ball pulls on it, but because the surface it's moving on is curved. This was Einstein's key insight. Gravity is geometry. It's the shape of space-time. This idea became general relativity, published in 1915. It didn't just modify Newton's laws. It replaced them entirely. And it made predictions more accurate than anything physics had ever seen before. Part 5. Predictions that proved Einstein was right. Einstein's theory didn't ask for small adjustments. It predicted effects that sounded outrageous. Light bends when it passes near massive objects. Time runs slower in stronger gravitational fields. The orbit of Mercury would shift in a way Newton's laws couldn't explain. Massive stars could collapse spacetime so completely that not even light could escape. The universe itself might be expanding or contracting. One by one, the evidence rolled in. 1. The solar eclipse of 1919. Scientists recorded starlight bending around the sun exactly as Einstein predicted. Newspapers declared him a genius overnight. 2. Mercury's orbit explained. For decades, physicists struggled to explain a weird drift in Mercury's orbit. Einstein solved it instantly. 3. Clocks run slower near gravity. Atomic clocks in tall buildings tick slightly faster than those at ground level, exactly matching Einstein's equations. 4. Gravitational lensing. Massive galaxies act like cosmic magnifying glasses, bending light in dramatic arcs we can now photograph. 5. Black holes and the expanding universe. Einstein's math predicted both. And today, we have overwhelming evidence that both are real. Einstein didn't just tweak physics. He created an entirely new framework that describes everything from planetary motion to the life and death of stars. Part 6. How relativity became part of everyday life. It's easy to think of relativity as something abstract or far removed from daily life. But without it, modern technology simply wouldn't work. Here are a few ways relativity affects you every single day. GPS satellites. GPS works by comparing the time signals from over 30 satellites orbiting Earth. But here's the problem. Satellites move fast, their clocks run slower due to special relativity. Satellites experience weaker gravity, their clocks run faster due to general relativity. Without correcting for both effects, GPS signals would drift by kilometers every day. Your phone would have no chance of knowing where you are. Relativity keeps your navigation accurate. Electronics and particle accelerators. Whenever particles move near the speed of light, like inside the Large Hadron Collider, relativity dominates their behavior. The machines must be designed using Einstein's equations, not Newton's. Nuclear energy. E equals mc squared explains how small amounts of mass can convert into huge amounts of energy. This equation powers nuclear plants, medical imaging, and parts of astrophysics. Modern astronomy. Black holes, neutron stars, gravitational waves, the expansion of the universe all depend on relativity. We're not just living in Einstein's universe. We're using it. Part 7. Time isn't what we thought. One of the most profound consequences of relativity is that time is not universal. It doesn't flow at the same rate for everyone. It depends on your speed, your altitude, your gravitational environment. If two identical twins lived differently, one staying on Earth and one traveling at near light speed for a year, when they reunite, the traveling twin would be younger. This is known as the twin paradox, and it's a direct consequence of relativity. It isn't science fiction. It's been tested with precise instruments and fast-moving particles. The effect is small at human speeds, but very real. Time is flexible, elastic, shaped by your motion and location. Einstein discovered that time is not separate from space, it's woven together with it. Part 8. The shape of the universe. General relativity doesn't just apply to planets and clocks. It describes the structure of the entire cosmos. In Einstein's universe, space can stretch. Time can slow down or speed up. Gravity is curvature. Black holes bend space-time infinitely. Light follows paths through warped geometry. The universe can expand like a balloon. Einstein's equations provided the framework for the Big Bang theory, cosmic inflation, and the discovery of dark energy. Even today, the largest observatories and scientific missions rely on relativity to understand what we're seeing. Einstein's ideas reached farther than even he imagined. Part 9. The limits of relativity. As powerful as relativity is, it has boundaries. It doesn't describe everything. When physicists try to combine relativity with the rules of quantum mechanics, our other major theory, they conflict. General relativity works at the scale of galaxies and stars. Quantum mechanics works at the scale of atoms and particles. To truly understand reality, we need a theory that merges the two. Some believe string theory or loop quantum gravity might be the solution. Others think we're still missing a deeper insight. Einstein gave us the framework, but the story isn't finished. Part 10. Conclusion. The discovery that rewrote reality. Einstein didn't set out to be a legend. He wasn't wealthy, famous, or even employed as a scientist when he made his biggest breakthroughs. He simply asked a question: what would the world look like if I rode alongside a beam of light? That simple question tore open a new chapter in physics. Relativity didn't just adjust our understanding of time, it reinvented it. It showed us that Time is not constant. Space is not fixed. Gravity is not a force. The universe is dynamic, flexible, and interconnected. Even reality itself depends on where you are and how you move. More than 100 years later, Einstein's ideas remain some of the most accurate, tested, and successful theories humans have ever created. And they all began with a young man, a quiet office, and a mind that refused to accept the boundaries of conventional thinking. This is the discovery that changed time itself. And it continues to shape our understanding of the universe every single day.